All right, welcome back to part 2 of the friction notes video. We're going to do some more examples here. So in this case, we got Jack, Jason, John, and Johnny are practicing hockey on a frozen Bluebird Lake. Not sure where Bluebird Lake is. Maybe it's not even in Georgia if it's frozen this time of year. But it's Jack and Jason chase after the 0.162 kilogram, aka 162 gram puck. It decelerates, so we're slowing down, from 10.5 meters per second to 8.8 meters per second in 14 seconds, right? So we got initial velocity, we got a final velocity, and we got a time here. So throwback to some kinematics days, right? We got a mass here. So one thing I really like about AP Physics is it combines problems from multiple units, right? You got to really understand physics from the beginning to the end to be able to solve AP problems because they pull on lots of different chapters and units. They really build on one another. So this problem starts out as a kinematics problem, okay? At the beginning here, we could have solved this problem in the last unit, okay? Because we're trying to find the acceleration of the puck. So if you know, acceleration is defined as your change in velocity over time. And keep in mind, that's always final minus initial, right? So your final velocity is 8.8. Your initial velocity is 10.5. And that takes a time of 14 seconds. It's a long time for this puck to go. So remember, if you're going to do this in one step in your calculator, the top needs to go in parentheses because that's all in the numerator. Okay, so 8.8 minus 10.5, all divided by 14. Gives us an acceleration of negative 0.121 meters per second squared. Okay, so that didn't even really involve forces or anything at all. Okay, just finding the acceleration was a straight up kinematics problem. Part B says determine the force of friction experienced by the puck. So in this case, our puck is moving. So this is going to be a kinetic friction, not a static friction. So force of kinetic friction there. So as usual, you want to draw a little free body diagram. Maybe you're feeling artistic today and you can draw a hockey puck. That's about as far as my artistic ability goes. So there's my puck. I'm sure yours is much better than mine. We know we got weight acting down on the object, mass times gravity. We know we got normal force acting up on the object. We'll call that Fn for this time. Just like the Ford coupe that we had in the last problem, if a hockey puck is in motion, it's going to stay in motion. We do not need an applied force going forward here. We're simply going to have a frictional force going backwards, slowing us down. Okay, notice usually we assume that ice is negligible friction, but in this case, we're told that the hockey puck slows down. Okay, so we know there has to be some friction acting on it. If you look ahead in the problem, it says it's bumpy ice, right? So maybe it's not so smooth. It's got some imperfections in it, so there's a little bit of friction going on here. Okay, so in the x direction, our net force is not 0. Some of our forces in the x, it's unbalanced. Clearly, we only have the force of friction going backwards. So we're going to use Newton's second law in that case. Not sure where that 5 came from. Another key is that if we accelerate, that tells us it's second law, our unbalanced forces. Okay, so none of these players are pushing the puck forward. They're chasing after it. Right, it already got hit previously, and it's already sliding across the ice. In the y direction, our net force will be 0. The puck is not going up or down the lake, it's going across the lake. Okay, so the force of friction here, experienced by the puck, that's in the x direction. There's only one force there, right? We don't know the coefficient of friction between the puck and the ice. So we cannot use this equation, right? Our kinetic friction equation. I use Fn in this problem. We cannot use that one because we do not know our coefficient of friction. right? So since we don't have this, we can't use this equation. That's not going to work. But we can use Newton's second law. Okay, so if we revert to Newton's second law, we know the net force in this case is only the frictional force. And that's the only force causing a horizontal acceleration. Right, so in this case, our force of kinetic friction is just going to be equal to the mass times the acceleration, which we know both of, right? Our mass is 0.162. Keynote, you should always put the leading 0 on your numbers that are decimals. That way they know that you know it's a decimal and that your decimal point isn't just a stray mark. So if you have that leading 0, it makes everything crystal clear and unambiguous. So we got our acceleration from the last part, negative 0.121. If we multiply those together, we get a force of negative 0.02 newtons. Okay, so a very small amount of friction, right? We are accelerating very slowly, 0.12 meters per second squared. That's not a lot of acceleration, right? Remember, this negative sign just means backwards. Okay, so that tells us our magnitude is 0.02 newtons and our direction is backwards. Okay, our puck is slowing down. So the magnitude of the force is 0.02, the direction is backwards. So 0.02 is the amount, backwards is the direction. All right, part C, determine the coefficient of friction between the bumpy ice and the puck. So now is when we want to use our previous equation, right? So I'm just going to slide this down, be lazy so I don't have to write it again. We want to use this equation because now we're looking for the coefficient of friction. We have the frictional force, and we can find the normal force because we know the net force in the y direction is 0. Slide that down as well. So we know that the normal force going up has to equal the weight going down, which is 0.162 times our magical 9.8. Hopefully you know by now 9.8 is not a force, it's an acceleration. That gives us a weight of 1.59 newtons, which is also the normal force. Okay, so we can plug that back into our equation here. So we got our FK from part 1. We got our normal force, from part 2 and part 3. So if we plug those in, 0.02 newtons. Notice I don't need the negative there because this equation just tells us the magnitude. Your coefficient of friction will never be a negative number. UK, and then our normal force is 1.59 newtons. Notice I rounded off 1.5876 on my calculator to 1.59, but I will keep that whole number in there when I do the calculation. That way I'm not really rounding until the end. So divide that over to the other side, divide that over to the other side, and we're going to get a really small number because it's ice. And we get 0.0124. So that's going to be our final answer here. That's our coefficient of friction between the puck and the ice. Notice it's very small, right? Only 1% of our force actually gets turned into friction, right? So the normal force is pretty large compared to the amount of friction, so it's a very small percentage. All right, here's our next problem. A force of 27 newtons is required to start a 3.8 kilogram box moving across a horizontal concrete floor. Keyword here is start. So that tells us that the box is initially at rest and we want to get it moving. So that tells us that we are dealing with some static friction here. Another key hint that we're dealing with static friction is that it says static friction. So that's a little bit more obvious. But if it didn't say that, then you would need to infer that if we're starting the box, that means it's initially at rest. So static friction is at play. So remember, static friction can change values based on how hard you push, right? So if I push this box with 10 newtons of force, there'd be 10 newtons of static friction. If I pushed with 12, there'd be 12. If I pushed with 19, there'd be 19. If I pushed with 27, that's going to be the maximum amount of static friction that the box will experience before it starts to move. Okay, so that's kind of that main or maximum value. If you remember, your equation has less than or equal to in it. Okay, so my static friction value can increase up to this maximum or threshold value of 27 newtons, right? So 27 is our threshold value. So our box here is 3.8 kilograms. So once again, start with a little free body diagram here. So we know we got weight going down. I'll call that FG this time. Remember, there's several different names for this force. I got the normal force going up. I used capital N a second ago, so I'll use that ahead. In the Y direction, our box is not accelerating up or down. So our net force in the Y is going to be 0. Those two forces need to balance. All right, in the X direction, we are applying a force horizontally, pushing it forward. And we're told that's 27 newtons. If you want to go ahead and put that on your free body diagram, you can. If you want to leave that off for now, then you can as well. You can just label the names of the forces. And then in this problem, since we are just starting the box is at rest. It wants to remain at rest. This is a first law problem. Okay, anytime that we're starting an object at rest, that's first law. Okay, so until we can actually get it moving, it's going to remain at rest. Okay, even though we're applying a force to it, there's going to be a balanced force in the opposite direction. Okay, so there's going to be a frictional force going backwards, and that is Fs for static friction. So that also tells us that our net force in the X direction will be 0 as well. So our forces will be balanced. So if we got an applied force of 27 newtons going forward, that means our frictional force going backwards, they have to cancel out. So our applied force equals our frictional force equals 27 newtons. That was given, okay. So we know our frictional force here, right? We know that. We're looking for our coefficient of friction up here, which means we need the normal force. Hopefully you realize by now that the normal force and the weight are equal to one another. Since our net force in the Y direction is 0, Fg equals our normal force. These random lines keep coming up. So we got mg equals n. Our mass is 3.8. Gravity is 9.8. Mass to weight multiplied by 9.8. So we just put that in the calculator. 3.8 times 9.8 is 37.24 newtons. Right, so that's our normal force and our weight. So if you want to put that on your free body diagram, feel free. If you don't want to, that's okay too, as long as your forces have names and arrows. That's mostly what we're looking for here. Okay, you don't have to put the numbers on there if you don't want to. So we're looking for our mu here. So we got our other values. So let me switch colors here. About a nice purple. So we know our frictional force is 27. We know in this case, we can use an equal sign because that is the amount. It can go up to 27. In this case, it's equal to 27. We got our mu s, and we know our normal force is 37 0.24. All right, so we just got to divide that to the other side. So if we do the math, our mu s is equal to 27. That is 0.725. Remember, unitless here. So in order to get this box moving, you have to exert a force equal to 72.5% of its normal force, which is also in this case 72.5% of its weight. Since we're pushing horizontally and on flat ground, our normal force and our weight are equal. Later this unit, we'll get to angled forces as well as angled surfaces, which will change this calculation a little bit. All right, part B, the 27 Newton force continues. The box now accelerates at 0.5 meters per second squared. So now we got an acceleration. That tells us we got a net force, and Newton's second law will apply. Okay, so once we get this object moving, 27 newtons is enough to break free of that static friction. Now, kinetic friction takes over, right? We're sliding the box across the floor. So our net force in the x direction will not be 0. We've got to use MA here, Newton's second law. Notice, every time I do a problem, I start with either net force is 0 or net force equals MA. On the AP exam, that will often get you 1 point on a problem, simply writing F net equals MA or F net equals 0 for a particular direction. So definitely always start with that and then apply the specific forces in your situation. So in this case, we need a quick free body diagram. Again, we got our applied force here is still 27 newtons. We know our weight here is still 37.24. That didn't change. Didn't put anything in the box. We know our normal force here is still 37.24. Notice these two arrows vertically are about the same size. You can use kind of different scales on the X and the Y axis. So on the X, I'm just showing that they're about the same size. I'm not trying to show that this 37.2 is way more than 27 or way less, right? The arrows, as long as they match on each axis, that's fine. So these two are about equal, so I drew them about the same size. The applied force is 27 here. We know there has to be less force going backwards from friction. That's going to be my FK. So I'm going to draw that arrow noticeably smaller to show that we are accelerating in this direction, right? So if you want to draw an arrow off to the side that shows which way you're accelerating to remind yourself, that's okay. Make sure all of your force arrows are actually attached to your object in your free body diagram. And if you're going to do an acceleration, make that off to the side. Okay, don't include acceleration on your free body diagram because it's not actually a force. Okay, it's caused by a force, but it is not a force by itself. That's like 9.8 is not a force. It's an acceleration due to gravity. All right, so we're looking for the coefficient of kinetic friction here. So we know we are accelerating at 0.5 meters per second squared. We know the mass of our box from earlier up here. That's our mass. We got to do our net force in our x direction. So in this case, we got a forward force that's applied, FA. We got a backwards force that's friction, kinetic in this case, since it's sliding. It's going to equal M times A. All right, so our applied force we know is 27 newtons. We know the equation for kinetic friction is mu K times the normal force. So I will just go ahead and plug that in. And mass we know is 3.8. And our acceleration is 0.5. All right, so we got 27 over here. We know our normal force is 37.24. We can do the math over here as well. So notice we're going to end up with a negative sign here. So we're going to flip-flop these terms. So we got 27 minus 3.8 times 5. If you want to do that as 1.9, that's fine. And let's do the other side. K times your normal force of 37.2. All right, so we've rearranged the equation to get mu k on one side by itself. All right, so I subtracted this over to the other side, subtracted this whole term to this side. So they just flip-flop each other. All right, so to get mu k by itself, we got to divide by 37.24 by this whole thing by 37.24. Make sure you divide the entire numerator in parentheses in your calculator if you do it all in one step. 27 minus 3.8 times 0.5, those parentheses. And we get mu k, the coefficient of kinetic friction, is 0.674. So when it was still, right, static friction converted 72% of its weight into friction. When it's moving, kinetic friction only converts 67%. Okay, because an object at rest wants to stay at rest. That's going to be more friction. Once an object's in motion, it wants to stay in motion. So there's going to be less friction between the box and the ground. Okay, so 67% versus 72%. Hopefully that makes sense. Hopefully you worked through it on your own and you understand where we're going. And we will go on to the next one right now. All right, this is the last problem we're going to do in this video. Go ahead and pause the video, come up with the answer on your own. This is actually an old AP multiple choice test question. So you should try and answer these in like 1 to 2 minutes tops, because you're going to have 90 minutes to answer 50 questions. So about 1.5 minutes should be all you should spend on the multiple choice questions. So go ahead and pause the video and answer on your own. I'll be back in 5, 4, 3, 2, 1. All right, the answer to this question is D. Hopefully you're able to do it in a minute or two. Okay, we got unbalanced forces here. So our net force in the x direction is our frictional force, and I made it negative because it's to the left. It's slowing us down. It tells us it's to the left, right? We know the equation for the friction is mu times the normal force. We were given the mu of 0.2, and the normal force is 40 newtons. That equals m times a. We don't know the mass of the box, but we know that 40 newtons is m times g. Remember, in the AP exam, you can always use 10 for gravity. When it says most nearly, they're just using 10 as gravity as a quick approximation. If you use 9.8 or 9.81, you'll get a more accurate answer. But they just want these type of questions to be done quickly. We call it kind of back of the envelope style. So we're estimating the closest answer to the correct answer here. So our m times a, we got to solve for a, so we divide m to the other side. We solve for m by doing the weight over the gravity. So it's mu times the normal force. So negative 0.2 times times 40, divided by the weight over gravity. So really the 40s kind of cancel out if you're doing the math, right? 40 on the top, 40 on the bottom goes away. We're dividing by 1 over 10, which is the same as multiplying by 10. So our final answer is negative 2 meters per second squared. In this case, 2 is to the left. Okay, so our acceleration is in the direction of the net force. So D is the correct answer. Hopefully, just by looking at the problem, you're able to eliminate choices A and C, because it's definitely not accelerating to the right. Okay, then it's a matter of calculating if it's actually 1 or 2 as your correct answer. So that wraps us up for today. Next time we'll get to some angled problems, but hopefully you're able to catch up and follow along, work on your mastering physics, and I will talk to you tomorrow.